Review of the nervous system. The neurons. Right, here's a picture of a neuron. You see the cell body with the dendrites coming out of the head, or the major part of the body, the long axon, which is covered by a myelin sheath, and at the bottom, the terminal branches of the axon. The myelin sheath, which is around the axon, provides insulation, and probably just as important, it makes it possible for the nerve impulses to proceed very rapidly and smoothly down the axon. The myelin is produced in the central nervous system by the oligodendroglia or the oligodendrocytes. They're both the same thing, just two names for the same thing. In the peripheral nervous system, the myelin is produced by the Schwann cells. Transmission of neural impulses. Well, first, it depends on polarity. And here we're talking about membrane potential. The difference in electric charge between the inside and the outside of the cell. That's the neuron. That's what we mean by membrane potential or polarity. At rest, the cell is polarized. Inside the neuron cell is more negative than outside it. So here we see the resting membrane potential. That is the polarized cell. There's the two other stages here, the depolarization phase and the repolarization phase. During depolarization, there's a rapid shift of sodium ions into the cell, and that generates an electrical impulse. It triggers the release of neurotransmitters at the end and into the next neuron. On this diagram, you see the one area that is circled and shaded, and that area of depolarization is going to continually work down the shaft of the axon to the right. So the next phase, which is following immediately after that, is repolarization. Potassium ions move out of the cell, and that returns the charges to the membrane potential. So the sodium and potassium are on the wrong sides of the cell. So there's a pump that uses energy, but it returns to the electrons to their original position. And all of these, the membrane potential, the depolarization, the repolarization, the sodium-potassium pump, all of these are going on at the same time. All right, the synapse, it's the gap between the neurons. You see, it's like the bottom of one is attached to the top of the next one, and it is where the information is passed from one neuron to the other. That can be done electrically, it can be done chemically. Here's a more close-up version. We have the presynaptic terminal. That means the first one, where the impulse is coming from. Then there's a cleft, an open space between the two. And then we go over to the right, which is the postsynaptic membrane. That is the neuron that is receiving the message. This is done in a large part through neurotransmitters. There are multiple neurotransmitters out there. There's amino acids, there's peptides, there's monoamines. One of them is dopamine. Dopamine is a monoamine, and it is involved in the physical motivation and voluntary movement. When we don't have enough dopamine, that's associated with Parkinson's disease. Serotonin, on the other hand, is formed from the amino acid tryptophan, and it affects mood and anxiety. It's the feel-good chemical. It helps people to sleep. It helps them to perceive pain and to moderate the pain. It also helps with body temperature, blood pressure, and hormonal activity. But we think of it mostly as the feel-good chemical. Acetylcholine within the brain it helps with attention and cognitive functions, especially memory. In the cholinergic pathways outside the brain, it is the main neurotransmitter in the parasympathetic nervous system. Norepinephrine, which is also called noradrenaline, is a monoamine neurotransmitter, and it is associated with excitation within the brain, person having better attention, arousal, elevated mood. Outside the brain, it is the major player in the sympathetic nervous system. Then we have the enkephalins and endorphins. Those are the opioid type neurotransmitters. They modulate pain, they reduce stress, they also will depress physical functions such as breathing, that's what opioids do. And it is possible to have physical dependence on these. Think about the runner's high. That's what this is. People who run and get this endorphin release, they gotta have it. There's a physical dependency in some people. All right, let's look at the central and peripheral nervous systems. Here's a diagram of how they all fit together, and we're going to be breaking these down into pieces. The central nervous system, also known as the CNS. We see the central nervous system is made of the brain and the spinal cord. And here's a diagram of the brain with all the different lobes labeled. I'm going to refer you to your book for more on the different lobes, and also to the site that I've linked to your assignments that talk about what the different lobes do. Here is inside the brain, the hypothalamus, part of the midbrain. Right or left brain? Left brain is associated with language, math, logic. The right brain is associated with imagery, face recognition, music, and spatial abilities. So which one of these, the right or left brain, is utilized more in traditional education? Yes, it's the left brain. All right, the spinal cord. My question is, what is the cauda equina? Well, first of all, that's Latin for horse's tail, because it kind of looks like one. They are the nerves that branch from the bottom of the spinal cord. On this diagram, you can see where the spinal cord ends. It's only part way down the spine. The cord itself is shorter than the vertebral column, and what comes beneath it is the cauda equina. It's a branch or a bundle of nerves, but it is not the spinal cord itself. So, what is the blood-brain barrier? There is no single membrane that acts as this barrier. There's no single entity that is the barrier. The barrier is the decreased permeability of the capillaries that supply the brain. This decreased permeability restricts the access of different substances into the brain. They can't cross from the blood into the brain. The decreased permeability restricts the access of large molecules, molecules with low lipid solubility, and molecules high in electrical charge. They just can't cross the barrier into the brain. So this protects the brain from foreign substances, hormones, and neurotransmitters in the systemic circulation, and major changes in the environment of the body.